We're going to hear now from Dr. Eric Brown. He's a research staff member, and he's manager of the IT J.T. Watson Research Center. And since 2007, he's been the technical lead on what's called the Deep QA project at IBM. And that's the application of automatic open domain questioning and answering to build up the Watson system. And that system that he led in building was quite successful in the very highly popularized Jeopardy victory. So Eric has also published all kinds of articles in various journals, conference papers, and he holds patents in a number of areas, especially having to do with computer-based question and answering. So ladies and gentlemen, please welcome Dr. Eric Brown.
Thank you. Good morning. I am delighted to be here to talk to you about Watson. And so you just heard a little bit about Watson, but in the next 45 minutes, I'd like to take you a little deeper under the covers there. But let me start by talking about IBM. So last year, in 2011, IBM celebrated our 100th anniversary. And so for a technology company, a computer company, 100 years is actually quite an accomplishment. And if you look back over our history, there's a very rich history of innovation. Many of you may not know that IBM started in 1911 making some of the world's best cheese and meat slicers. And then we moved on to a little more technologically inclined machinery, creating tabulating machines, which were actually crucial for supporting some of the censuses that were being taken at that time. And then we advanced to punch card readers, making some of the best punch card readers in the world, and ultimately making the Social Security system in the United States possible. And then as we move forward in the century, we have the IBM System 360, really the first commercially viable business computer. Moving on from that, we have advances like the relational database in 1970, the Fortran programming language, which was really critical for supporting science and scientific programming, the RISC computer processor, the reduced instruction set computer, which is really now the foundation of a lot of our electronics. And so with this rich history of innovation, what better way to celebrate 100 years than to build a computer that would play on a TV game show? And so this, of course, is what IBM did. And what I'd really like to do, though, is explain to you why, if we can build a machine that can actually compete on Jeopardy, which, to be more accurate, is America's favorite quiz show, we've actually accomplished something that's very interesting. So let me start with the basic problem. What we really want to do is create technology that can help humans make better decisions. We want to make us more efficient. We want to give us access to more knowledge, and in particular, access to knowledge the way humans naturally communicate and record that knowledge, which is text. And so text is an example of what we call unstructured information. And as we're all aware, this kind of information is just growing so rapidly and represents such a large amount of the data that we want to leverage. It's a big challenge. And what I'm showing you here is two kinds of data. On the right-hand side, more traditional data, structured, transactional, and we have a pretty good handle on managing that with databases, for example, relational database technology. The problem with that is it tends to get a little brittle when you want to deal with a wider variety of kinds of information. You have to design the schema, you have to organize it more manually, and you run into some challenges if you want it to scale. Contrast that with the left-hand side, where we have completely unstructured information and techniques for managing that, such as search engines. Imagine your favorite web search engine, and then moving up to more sophisticated analysis, such as open domain question answering. And so now on the left-hand side, we can access and search a much wider variety of content, but that search and access tends to be more shallow. And what we really want to do is get the best of both worlds and have something in this sweet spot that gives us deeper understanding, higher precision, and really broader, timely coverage, all at a much lower cost. And so this is what Watson is designed to do. And the starting point is really this question answering technology. And we've been doing research in question answering for several years. We started in the late 90s, but around 2005, the performance of that technology had plateaued, at least within our research group and with the limited investment that we were making in it. And we realized that if we're going to advance this question answering technology in a significant way, we need to elevate it to something we call a grand challenge problem. And this would allow us to invest a little more resource, put a little more focus into it, and really try and tackle this problem and create some leading-edge technology. And so at IBM, we like to explore grand challenge problems every once in a while, and they have a few key characteristics. So one, of course, as scientists, we want to be driving important scientific advances. And in this space, we're looking for ways for computers to impact society and science. As a company, we're interested in technologies that are relevant to our customers. And so if we think about supporting decision-making and technologies to access all that unstructured information, there's a whole bunch of areas there like business intelligence or knowledge discovery and management that this technology could be applied to. And then, of course, as a grand challenge problem, we want to capture the broader imagination. And we want to look at problems that really appeal to people. When they see it, they go, aha, I know that's a hard problem, and what you've done is really very interesting. And a previous example of a grand challenge problem might be the Deep Blue chess playing system. And so in the mid-90s, building computers that could play chess was an interesting topic in artificial intelligence. But people never believed or were skeptical that we could create a computer system that could beat a grand champion at chess. And in fact, in 1997, IBM's Deep Blue computer was victorious over Garry Kasparov, the chess grand champion at the time. But if you think about chess as a grand challenge problem and contrast that with decision-making, leveraging knowledge the way humans naturally communicate it and record it, there's a big difference. So chess actually, as far as building a computer program to play it goes, tends to be fairly finite, mathematically well-defined, and ultimately grounded in fairly explicit, unambiguous rules. This is much different from human language, where it's ambiguous, contextual, and implicit. And so now, as humans with a brain that's been trained to understand language from birth, we're able to communicate very rapidly with each other. But what we don't even realize is that we leave an awful lot unsaid, so things tend to be implicit or tacit. And moreover, we're very creative in our use of language and can use the same word or phrase to mean many different things, which makes it ambiguous. And so dealing with human language is a big problem. Now, if we want to come up with a grand challenge problem to test and drive this technology, what better grand challenge problem than Jeopardy? And it actually is interesting along 5 key dimensions. So first, Jeopardy addresses this broad open domain of knowledge. So as this television quiz show, if you haven't seen it, there are 3 contestants playing, and there's a board of questions that at first, all you see is the dollar value. A contestant selects a clue based on the dollar value. The clue is revealed. The host, Alex Trebek, reads that clue. And then if you think you have the correct answer, you ring in and attempt to answer it. If you get the clue right, the value of the clue is added to your score. But if you get the clue wrong, the value of the clue is subtracted from your score. So that's Jeopardy. And it covers topics from ancient history to geography to science to politics. And I have 5 examples of real Jeopardy clues here. So now this is the interactive portion of my presentation. For $200, the juice of this bog fruit is sometimes used to treat urinary tract infections. Cranberries. That's almost correct. If you've watched Jeopardy, you know that the correct way to phrase your response to a Jeopardy clue is, what is cranberries? Very good. For $400, this might be a little tricky. Portland, Oregon is the city of these flowers. We're looking for roses. For $600, in cell division, mitosis splits the nucleus and cytokinesis splits this liquid, cushioning the nucleus. Any chemists or physicists, biologists out there? We're looking for cytoplasm. For $800, Grace Murray Hopper is credited with applying this 3-letter term to a mysterious computer problem. What is a bug? All of the IT people out there got that very quickly. And then finally, for $1,000, an early name for Google was this type of massage. And those of you familiar with the history of Google will know that we're looking for back rub. So 5 real Jeopardy clues, and just from that handful of clues, you see they cover a wide variety of topics, from home remedies to actual biology to computer terminology, questions about cities, and even questions about technology. The second dimension of Jeopardy is that these questions are expressed using complex language, and you can see that just from these handful of clues here. The third dimension is the need for high precision, and so this really distinguishes this challenge from just search. It's not enough to do a search and find 1 or 10 or 10 million documents that might contain the answer to the question. Rather, we have to dig down into those documents, pull out the precise answer, and return that as our response. Alex Trebek does not have time to read your web search hit list or even the top document, even if you guarantee the answer is in there. So we have to come up with precise answers. The fourth dimension is the need for confidence. As I mentioned, if you get the clue wrong, you're penalized, and the value of the clue is subtracted from your score. So it's essential to not only come up with an answer, but to come up with a confidence in your answer, which means looking at one source for that answer may not be sufficient. You need to consider a variety of sources and a lot of evidence to evaluate that answer and decide if you're even willing to weigh in with that answer. And then the fifth element of the problem is the need for speed. And on average, there's about 3 seconds available to understand the question, come up with possible answers, examine all of the evidence to support those answers, come up with a confidence in that answer, and then ring in and try and answer the clue. So let me go back just a second here. No, can I go back? Oh, there we go. And so I want to give you one more example of a clue here. And this clue comes from American Civil War era history, and the category is Lincoln blogs. And so now this is a little specific to the United States, but the clue is Secretary Chase just submitted this to me for the 3rd time. Guess what, pal? This time I'm accepting it. Secretary Chase just submitted this to me for the 3rd time, pal. Guess what, pal? This time I'm accepting it. And so I flashed the answer there just for a moment, so you may have seen it. But the correct answer we're looking for there is his resignation. And so now this clue is a little tricky because it requires fairly detailed knowledge of Civil War era history. And so if you know that, you'll know that Secretary Chase submitted his resignation. If you didn't know that, however, you might look at that clue and just analyze for what it's asking. And you know that you have a secretary submitting something to their president. And what might a secretary submit to their president? It might be a speech, it might be a bill, or perhaps we're cynical about politics and we'll just assume that it's going to be his resignation. And we might come up with the answer that way. So now, in the spirit of the previous panel, I like to go out to middle schools and high schools and talk about technology. And I was presenting Watson to some middle school students, talking about this very clue. And again, we're talking 6th, 7th, and 8th graders who may have studied Civil War history for the United States, but not necessarily have knowledge for this particular clue. I threw it out there, however, and not expecting a response, but one girl in the 6th grade raised her hand, and her response to that clue was, "What is a friend request?" And so when I first heard that, I thought that was interesting, funny, but she was being very brave and kind of risking it to go in front of her peers and throw out an answer. But the more I thought about that answer, the more I really loved it. And let me tell you why. 2 reasons. First, it really makes a statement about kids and technology and what they're growing up with. So, if you're a parent, you're intimately familiar with this. Middle school kids are steeped in social media. Facebook is just always on their minds. And, well, I thought, if Lincoln had Facebook back in 1864, he very well may have been friends with Chase, at least until he submitted his resignation. But it talks about how children are growing up with technology, And for me, as somebody working for a commercial company, it's a statement about what our potential customers, what their expectations are about technology and how we're going to be delivering products and services. And it also makes a statement about potential employees and their expectations about how we're going to use technology to help them do their job. And social media is just fundamental to that as these kids are growing up with it. The second aspect of this is more about natural language and understanding and how it is so contextual. And you look at the words submitted and accepted, and as adults, those words might have strong associations with resignation. For a sixth grader, those words have a strong association with a friend request and Facebook. And so when you're dealing with understanding natural language, the challenge is understanding that context and disambiguating words' meanings within that context. And not only that, the meaning of words can change over time. So this is at the core, the challenge of dealing with natural language and creating a decision support technology that can leverage that knowledge expressed in natural language. So let me take you through a few more examples here. Here's another clue from Jeopardy! In May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India. So now, if you think you know the real answer to that question, let's look at how Watson might analyze this and come up with its answer. So first, Watson is going to apply what we call a wide variety of natural language processing techniques. And when we talk about natural language processing for a computer, what we really mean is the process that humans go through to diagram a sentence. It's essentially the grammar that you learned in 8th grade. How do you identify the parts of speech? What's a noun? What's a verb? What's a preposition? How do you identify the sentence structure? What's the subject? What's the verb? What's the object? And so what you can see here on the left-hand side is how Watson might take that question and break it down into a sentence tree with the subjects, the verbs, the objects, and the individual keywords broken out. Now, with those keywords, the first thing you might do is search for passages that may contain the answer and use those keywords to support that answer. So I've done that here, and I found this passage. In May, Gary arrived in India after he celebrated his anniversary in Portugal. So based on keyword matching, we got a strong match between celebrated, May, anniversary, Portugal, India. That suggests that Gary is, in fact, the explorer that we're looking for here. So now, how many of you thought Gary was the explorer? Yes, hopefully not very many. I mean, who's heard of Gary, Gary the explorer? There's probably not the famous explorer we're looking for. In the United States, when we talk about explorers, we think Christopher Columbus, Magellan, or perhaps the correct answer to this clue, Vasco da Gama. And so now, here's another passage for that same question. On the 27th of May, 1498, Vasco da Gama landed in Caput Beach. Now, this passage contains the correct answer to the question, but the challenge is, how do we evaluate this passage as evidence to support that answer? And when you look at it, for starters, it only has a few keywords in common with the original question. And those keywords are prepositions like in, articles like the, and the word may. May is a month, and may is also an auxiliary verb, but typically don't tell us an awful lot about the meaning or the content of the passage. So if we're going to evaluate this passage as evidence for Vasco da Gama as the answer to that question, we're going to have to dig down more deeply and apply deeper analytics to come up with that evaluation. And so instead of just looking at the keywords on the surface here, we can drill down with something called temporal reasoning. And with that, know that if I'm celebrating the 400th anniversary of something in 1898, that event occurred in 1498, and I get a match. I can use something called statistical paraphrasing to know when two words or phrases can mean the same thing. So that arrived in can mean the same thing as landed in, and I get a match. And geospatial reasoning to know that Caput Beach is in Kerala, and Kerala is in India. And so after doing that reasoning, I also get a match. So now, by applying deeper analytics, drilling down beneath the surface form, beneath the surface words, and into the meaning and the context of the passage, I can actually evaluate this passage as good supporting evidence for Vasco da Gama as the correct answer. So applying these deeper analytics, natural language processing as well as text analytics that can find words or phrases that mean the same thing, do temporal reasoning, geospatial reasoning, and a wide variety of other techniques, we can then create the Watson system. Now, when we look at Jeopardy clues, it turns out that humans are actually pretty good at this task. And one of the first things we need to do as we start to build this system and evaluate it is have an appropriate metric for measuring the system's performance. And so what I'm showing you here is how we measure the performance of humans on this task. And we call this the winner's cloud. Each dot on that plot represents the performance of the winner of an actual Jeopardy game. And along the x-axis, the bottom axis, it says, within that game, what percentage of all of the clues did that winner attempt to answer? So with 3 players in a game, your fair share is 33% of the clues. The average Jeopardy champion answers, let's say, 50% of the clues in a game. So they get more than their fair share. The y-axis is showing their precision. For the clues they attempt to answer, what percentage do they get correct? The average Jeopardy champion gets roughly 90% of those questions correct. So those dots show average human performance on this Jeopardy task as we've defined it. Perfect performance would be in that upper right corner where you're answering 100% of the questions and getting 100% correct. The red dots are the games played by Ken Jennings. So Ken Jennings is our Gary Kasparov of Jeopardy. He's the Jeopardy Grand Champion, famous for winning 74 games in a row in 2004. Ken Jennings, when he's playing, he's answering more like 62% of the questions, so getting nearly 2/3 of the questions in the game, and getting about 93% of them correct. So he knows a lot, and he knows what he knows, and he's very precise. And in fact, there's one game there, that dot on the far right, where he's answered 82% of the questions in that game. And so if you saw that episode, that was just 2 other people watching Ken Jennings answer questions. And this is our target performance. This is what we set out as a goal for ourselves, to create a question answering system that could compete on Jeopardy at that level. That lonely brown curve in the bottom left there was our starting point. This was our state-of-the-art question answering technology back in 2007, something that we had been working on with modest investment since the late 90s, but representative of that performance that had plateaued. And what we really wanted to do was drive the performance up into that winner's cloud. And so that's where this Jeopardy Grand Challenge problem emerged. At the beginning, we had a few key philosophical commitments about how to tackle the problem. So first, large handcrafted models are not going to cut it. So what do I mean by that? One way to try and solve this problem would be to create ontologies that organize all of human knowledge in some organized way, with all of this data curated into that ontology. And now I've structured all of this knowledge, and assuming I can take an arbitrary question and map it into this structured knowledge, this ontology, I can answer any question. The problem with that approach is that, again, it requires way too much human engineering. It's too brittle, it's too narrow, it doesn't scale, it's not going to work in new domains. So that is not how we're going to do it. Instead, we want to leverage knowledge the way people naturally communicate it and record it, this as-is knowledge, and in particular text. To the extent that structured resources are available, we will, of course, leverage them. And we do that both in Jeopardy and in the new domains that we're exploring in business. But the emphasis is on natural language processing techniques for text. The second philosophical commitment here is what we call intelligence from the combination of many. There's no single technique that's going to be able to solve this problem. Instead, we need an overall architecture and a system that allows us to explore a number of different hypotheses simultaneously and apply a wide variety of analytic techniques to evaluate each of these hypotheses over a broad collection of evidence, and then ultimately combine all of these results in some meaningful way. That leads us to the third commitment here, an architecture to support integration and learning. We need an architecture from a software engineering point of view to combine all of these different techniques together, and then a way to combine the results of those analytics. So think of each analytic as an expert that has an opinion about a particular answer given a question. For some kinds of questions, this expert is going to be very good. For other kinds of questions, this expert may not be so good, but there are other experts that we'll want to consider. In order to figure out which expert to listen to, we use a machine learning technique where we will train the system and automatically learn how to combine the opinions or the weights of all of these different experts. This is what we mean by using machine learning to train the system. And then finally, the last point here is a scientific point that we want to drive the performance with measurement and analysis. And this is ultimately the only way we're going to know how well the system is performing, and we're going to be able to continue to drive up the performance. So what you see here is the overall architecture. I apologize, this is supposed to build out, but unfortunately it's already built out, so it somewhat obscures the architecture, but I can explain it to you anyway. Basically, there's a question in coming on the left, and final answers coming out on the right. And so I have a sample question here. Each year, the EU selects capitals of culture. One of the 2010 cities was this Turkish meeting place of cultures. That's going to get input into the first processing stage that we call question analysis. In that stage, Watson applies these natural language processing techniques to, again, parse the question, come up with the sentence diagram, the syntactic structure of the question, and identify a few key elements in that question. One of them is the word that describes the kind or type of the correct answer. And in this case, we're looking for a place or a city. And then to break that question out into what we call the focus of the question. Here, the focus of the question is rooted in that word place. And if I were to replace that whole subtree, the focus, with the correct answer, that would turn my question into a statement. After analyzing the question, it goes into a step we call hypothesis generation, which breaks out into a search phase and a candidate answer generation phase. So in this search phase, we're using techniques such as text search engines, knowledge-based searches, even some database searches, to come up with possible answers that we're then going to consider and evaluate. These are all these competing hypotheses. These hypotheses then go into an answer scoring and evidence evaluation phase where when we have our possible answers such as Essen or Istanbul or Sarajevo, we'll gather additional evidence for each of those candidate answers and evaluate that evidence using these deep analytics that I talked about. That bar chart there then gives us a way to visualize the weight that each of those different kinds of analytics is giving to each candidate answer. And then finally, by combining all of these expert opinions from these analytics for each hypothesis, we can come up with the final weighting and ranking of those answers. And you see that listed in the bottom right there, with Istanbul as the top weighted answer. So overall, this architecture leverages a number of techniques from a variety of disciplines that are loosely in the area of artificial intelligence. We have natural language processing, information retrieval, knowledge representation and reasoning, machine learning, deep analytics, and then ultimately to scale this system out and satisfy the latency requirements, we have parallel and distributed computing. And that actually leads us to an increase in performance of the system as we developed it over time. And on this chart, I'm showing you I'm plotting the performance of the system starting in late 2007 and then roughly on a quarterly basis until we get to the end of 2011, which was just prior to the actual exhibition match where Watson competed against Ken Jennings and Brad Rutter. And so by applying our overall development methodology, sticking to those early philosophical commitments, and leveraging this architecture, we're able to drive the performance of the system up until we're cutting through that winner's cloud, giving us a system that should be quite competitive. And to address the latency issue, not only do we use this parallel and distributed computing, but we apply it or leverage a distributed computing cluster built on top of off-the-shelf IBM Power 750 servers. And so here's just a summary of what that system looks like. And so for the exhibition match, and again, this is sized to play Jeopardy, a fairly specific task. We're using 90 IBM Power 750 servers that gives us 2,880 processing cores and 15 terabytes of main memory. Now, scaling this technology out over a cluster was essential. If we took the final version of the system, ran it on just a single processor, it might take up to 20 or 30 minutes to answer a single question. So taking 20 or 30 minutes to answer a question would, of course, make for a very boring Jeopardy game, and that really wasn't going to fly. But by using this parallel and distributed architecture and this IBM hardware, we're able to get that latency down to 3 seconds and actually have a competitive system, with the result being Watson's victory over Ken Jennings and Brad Rutter. And so if you saw the exhibition match in February of 2011, you would have seen this. But I'll just highlight again that at the end of the second game, Ken Jennings, who's on the left there, knowing that there was no hope of winning, when he placed his final Jeopardy wager, he also wrote in parentheses, "I, for one, welcome our new computer overlords." So, I think that's cute, but personally I think that's quite optimistic. We're nowhere near there yet, and there's still quite a ways to go. Now, of course, Jeopardy was a great public demonstration of the technology, but ultimately we're interested in applying this technology to business and solving real business problems. So there's a wide variety of areas we could explore. On the research team, which I'm a part of, we're interested in starting with the healthcare space and adapting Watson to the medical problem. Now, in medicine, there's this process of diagnosis called differential diagnosis, where a medical practitioner will come up with a number of competing hypotheses and then evaluate those independently, come up with tests that can help discriminate between them, and then ultimately make a decision. But this process of generating an hypothesis, coming up with possible answers, coming up with evidence to support or refute those answers, and then ultimately evaluating that evidence and making a decision is actually a paradigm that applies to any decision-making process. So while the research team is focused on medicine as our first domain, the result is an overall approach to problem solving that can apply to really any business problem. In the medical domain, however, there are several problems that we need to take a look at, and we start by addressing some sample questions here. So these are questions from a set called the Doctor's Dilemma test, which is almost a Jeopardy-like game run by the American College of Physicians for testing new interns. And so the questions are phrased in somewhat of a Jeopardy style, but of course they're medical, they're specific to medicine. So for instance, the syndrome characterized by narrowing of the extrahepatic bile duct from mechanical compression by a gallstone impacted in the cystic duct. Example of a medical question. Or syndrome of sore throat, fever, sepsis, and unilateral neck swelling. So these are the kinds of questions that we want to take a look at in the medical domain and use that to continue to drive the technology. Now, there are a number of issues that come up besides just understanding the questions and the terminology. There are things like causation. And so what causes something to happen? And if you're analyzing text and trying to understand these causal relationships, it can be quite tricky. So what could cause food to get stuck when you're swallowing, for instance? And what are the different ways to express that? There are issues of magnitude, a high temperature versus a fever, and how important is that magnitude? Or the chronology of these events occurring. Fever occurs after acute symptoms subside. There are issues like negation, so something that humans understand fairly easily and use quite freely, but if you are trying to develop computer systems that can understand and deal with negation, it can be a bit of a challenge. So you have something like productive cough versus non-productive cough, or if we're looking at an electronic medical record, a clinical note will often list a number of symptoms that the patient had, but may also say, and these were not found, fever, swelling, pain. But if you didn't notice the not found at the beginning of that, you might interpret that incorrectly and assume that those symptoms actually existed. Things like location, flank pain, lower back pain, kidney pain, knowing that all of these different references to location can mean the same thing or different things, all important to understanding the domain. There's also a challenge, a big challenge, with different ways to say the same thing. So I have a couple of examples here that demonstrate this. So in this first one, we're trying to come up with some dietary indiscretion. So attacks of Meniere's disease are precipitated by this dietary indiscretion. Now, in this particular case, the dietary indiscretion that we're talking about is actually a high sodium or high salt diet. On the right, I have a passage that actually suggests that salt and diet is related to this, but it says a low-salt diet might also help alleviating the symptoms of tinnitus and Meniere's disease. And so now, how are we even going to know that the dietary indiscretion here is related to sodium and that the indiscretion is a high-sodium diet and we can alleviate symptoms by having a low-sodium diet? So putting those two things together is a bit of a challenge. The second example is even much more complex. So we're looking for a drug treatment for nerve gas exposure that reactivates acetylcholinesterase. And now if you read the passage on the right, it talks about acetylcholine becomes prolonged, pralidoxime is the cure for organophosphate poisoning because it can cleave this phosphorylation. So now you have to know what a phosphorylation is, you have to know what cleaving that phosphorylation means, and then ultimately, if you interpret that in detail, you can actually relate that back to the original question. But how are we even going to develop technology that can do that? We could come up with a rule that addresses that specific problem in that second example, but how often are we likely to encounter that in future questions or problems? And so solving these kinds of problems is a big challenge. More generally, when we want to move from the Jeopardy domain to the medical domain, there are 4 key things that we want to explore. So first, in the realm of understanding, in Jeopardy, you're given a fairly specific question with an unambiguous answer. In business applications, and in the medical domain in particular, the input is not always a specific question, but rather a much richer set of what we call factors. And you could imagine even the entire electronic medical record being the input. The question may actually be fairly simple. What's wrong with me and how do I fix it? But the input is much richer than what we have in the Jeopardy domain. In the interaction column, rather than simple question in, answer out as we have in Jeopardy, we want to move to a much more interactive dialogue-based system where there's an input with a possible response and then the opportunity for refining the question, asking follow-up questions, and refining the answers. So interactive dialoguing. The third column there, explaining. Again, Jeopardy is fairly specific. You get to answer with your one top answer, and you're judged right or wrong, and then the game moves on. In a real-world application, we want to present the end user with a number of possible answers, and not just give them that answer, but also explain how the system came up with that. So access to the evidence that justifies that answer, and in particular, access to evidence from the literature, from textbooks, from journals, from conference papers, so that the busy physician who doesn't necessarily have time to keep up current on everything that's going out there in the medical research world can easily review the relevant evidence. And then finally, under learning, we want to make the learning much more interactive and real time. And so we have this sort of continuous learning and training process. Let me give you a couple of examples of those concepts here. So for something that we call Teach Watson, we're looking at ways for the system to interactively ask the end user questions and basically get smarter. So here we have this question, what neurological condition contraindicates the use of bupropion? And then we have some text on the right that might contain the correct answer. And in particular, we have text that says patients with pre-existing seizure disorder should not use bupropion. The question now, though, is what would have to be true for seizure disorder to be correct? And the problem is the question says contraindicates, but that passage says should not use. So unless we've already told Watson that should not use means the same thing as contraindicates, it doesn't know what to do. It can, however, detect this ambiguity and actually pose that ambiguity back to the end user as a question and say, does contraindicates the use of bupropion mean should not use bupropion? Or more generally, does contraindicates the use of mean should not use in general? And so here, in this approach we call Teach Watson, the system detects these ambiguities, but then generates questions to ask back to the user. This could be done interactively as the system is being used, or these kinds of questions could be captured, batched up, and then asked offline in more of a crowdsourcing approach. Here's another example of the interaction in the system, dialoguing to an answer. The input comes in, the medical record in the top left there, and the present factors, those that the patient has claimed they have as symptoms or the physician has observed, red painful eye, blurred vision, family history of arthritis, leads to this diagnosis. Behçet's disease is the top-ranked disease. However, as Watson analyzes the text to support other answers, such as Lyme disease, it discovers that Lyme disease is typically accompanied by a number of other symptoms. Those weren't even discussed. Watson can ask the medical provider, are these factors actually present? Is circular rash there? Is fatigue there? And if so, Watson can take that as input and refine its results and now actually prefer Lyme disease with much higher confidence. So the final element of this is providing access to the decision-making process that justifies these answers. And what I'm showing you here is just a sample user interface that could be created to support this overall diagnosis to treatment process that a medical practitioner could pursue. And so here you're seeing a layout with factors and symptoms on the left, and that CC is the chief complaint, the things that the patient is complaining about, along with other factors that may have come into play. And what you're seeing on the right is the current set of diagnoses that the system has come up with and its confidence in those diagnoses. And then moving on to drilling down into the evidence to support those diagnoses. Here we're considering 3 possible diagnoses: uveitis, iritis, and keratitis. And we can actually explore the evidence to support each of those diagnoses along different dimensions. So if we just look at symptoms, uveitis is preferred. If we look at family history, however, iritis is actually preferred. But then if we go back to, say, demographics, uveitis is slightly ahead. And then below that, you're seeing actual drilling down into the content that was analyzed to support evidence along those different dimensions. And then finally, the treatment options here, after we've come up with a diagnosis and collected additional information about the patient, confirmed that the patient has Lyme disease, but also observed that the patient is pregnant, and that suggests this particular antibiotic as the preferred course of treatment. So this is just a quick introduction into the possibilities with Watson and where we're going, and I hope that you found it interesting and enjoyable. Thank you.